3.2. Relationships between f and f prime. We'll get to all the other stuff here as we go. Relationship between the graph of f and f prime. Graph the derivative of the following function. Okay, so this is f of x. We're going to graph f prime of x here in red. And since this is a piecewise linear function, I'm going to take the slope here on this portion of the graph, which is consistent there. I believe it's positive 2/3. So the slope would be positive 2/3. So that would be f prime on that interval. Notice it's open there at 0 because there is no slope technically here at this point 0, 2. Alright, on the second portion of the graph, from here to here, it looks like the slope is -1. So on this interval from 0 to positive 3, we have a slope of -1. And then I believe, and on the final part of the graph, this slope along there looks to be 5/3. I believe it's 5/3, which is just a little bit less than 3. So from x equals 3 to x equals 5, we would have a slope of 5/3. So each of those separate graphs, the red, the green, and the yellow, would form f prime of x. All right, so let's look at a graph here, graphing the derivative from data. So sketch the graph of f that has the following properties. F of 0 is 0. Okay, so I'm going to plot that point right there. The graph of f prime, the derivative of f is shown on the left side, and f is continuous for all x. Okay, so this red piece tells me that the slope of my original function f is -1, and it's got to go through 0, 0, so I know that -1 through 0, 0 would look like that. And then it looks like at x equals 1, the slope changes. Okay, so at x equals 1, the slope changes, and it looks like that slope becomes 3. So that's what f would look like based on f prime's graph. So here we are. We're going to look real quick at one-sided derivatives. For a function to be differentiable at a point, the slope from the left must equal the slope from the right. Hence, the derivative from the left must equal the derivative from the right. Symbolically, that would look like that. So let's go ahead and show graphically and then analytically that the following function has a left hand and right hand derivative at x equals 0, but no derivative there. So again, the derivative from the left and the right must be equal. So here's a graph. Let's do x squared less than or equal to 0 and 2x. Okay, so you'll notice here at 0, these slopes are not going to be the same. It looks like the slope at x equals 0 for x squared. Okay, the slope looks like it's approaching 0, and our slope on the other side is 2. So those don't equal, therefore there is no derivative at x equals 0. So analytically, you can see what I've done here. I took our left side, which is x squared, used the difference quotient, sent h to 0, and I get this here, 2x plus h, for a simplified difference quotient. Clearly, as h goes to 0, that will disappear. So 2x, as we approach 0, we do direct substitution. Our derivative, right? Our derivative at x equals 0 will be 0. Now over here, on the second example, for 2x, right, I do 2x plus h, so that's f of x plus h. This is f of x all over h. Limit as h goes to 0 equals 2. Therefore, over here, f prime at 0 will be 2. And so because these two are not equal, the derivative does not exist at x equals 0 because of that inequality there, or non-equal parts. Okay, so does a function have to be continuous at a point to be differentiable at that point? The answer to that is yes. So the answer to the first part is yes. What if the function is continuous at that point? Must it also be differentiable? No, that doesn't have to happen. So like the absolute value of x, it's continuous here, but the derivative from the left and the derivative from the right are not equal. Alright, so the theorem of differentiability applies to continuity. If f has a derivative x, or at x equals a, then f must be continuous at a. The other way around, though, like we just said, is not true. Just because a function is continuous doesn't make it differentiable. Where do derivatives fail to exist? A function will not have a derivative at a point a comma f of a where the slope of the secant line fails to approach a limit as x approaches a. On the next page, we'll talk about a few examples. Alright, so an otherwise smooth function will fail to have a derivative. F prime of a does not exist at a point where a graph has a sharp corner. Example, absolute value of x. There's no derivative there. A cusp, right? This piecewise function, right? This piece, square root of x, and this piece, square root of negative x, would look like that. And at this point, there's no derivative. That's called a cusp. A vertical tangent line, like the cube root of x. The cube root of x looks like this. Okay, there is no derivative there at that vertical tangent. And a point of discontinuity, right? Okay, so this symbol right here means all x. So most functions we study are differentiable everywhere because they're smooth and continuous. Here's an example of those. All right, those are pretty easy to work with. This idea, though, of local linearity means that differentiable functions are locally linear if we can zoom in far enough, and the curve will become closer and closer to a straight line the further we zoom in. So let's graph this for a minute and find f prime of 0. So the absolute value of x plus 1 would be the absolute value of x shifted up 1 unit. Now, f prime of 0 in this case, f prime of 0 does not exist. Right? And the reason for that is because the derivative from the left and the derivative from the right do not equal. Today's technology is very useful in this way. We could find the numerical derivative of any function at any point using our calculator. So we're going to use we're going to press the math button and then use option 8. And what will come up is the option for you to be able to calculate the derivative. For example, this complicated function right here, which won't seem complicated later on. But to find the derivative at pi for that function, we use math 8. And it'll prompt you to plug in pi and the function and all that good stuff. And what you should get when you're done is a slope on that. So here's the notation that my calculator prompts me with. Okay, it asks me to fill in the variable of differentiation, which we're going with x for that, seeing that our function is a function of x as an independent variable. I'd type in my function here, and then once I type in the x here in dx, this green x auto-populates for me, and I just have to type in the input that I want my derivative taken at. And then what I get is f prime at pi is 0.292. So that would be the slope of my tangent line at x equals pi. So in example 6, again, we're going to use our calculator. There's a little bit more to this, though, to start with. First of all, we don't know the x value that we're trying to find the slope of the graph for yet. So what we want to do is, what I would do is, in y1 in your calculator, in y1 I would type e to the tangent of x minus 2. Okay, so what I would do, again, like I said, is I would type y1 in there as e to the tangent x minus 2 and find out where that crosses the x-axis. And what you end up finding is that at x equals 0.606 is where that graph crosses the x-axis. Now from there, what we want to do is, like I just did, we're going to type in dx, okay, input x there, we're going to type in f of x. Okay, and f of x is e to the tangent x minus 2. And then we're going to evaluate that, and this will auto-populate as x. And we want to type in 0.606. And then we're going to get out an answer which will give us the slope of the tangent line at that point for x equal to 0.606. With regards to rounding for the AP exams, always go out to 3 decimal places. So that's how I get 0.606. And then from there, I believe I get a slope of 2.959. So the intermediate value theorem says that on a closed interval a to b, if a function is continuous, then there exists a value x equals c such that f of c is between f of a and f of b. I know that this isn't a formal write-up, but that'll give you a little bit of reminder on the intermediate value theorem for functions. Okay, so now for derivatives, if a and b are any 2 points in an interval on which f is differentiable, then f prime takes on every value between f prime of a and f prime of b. This implies that in order for the intermediate value theorem of derivatives to work, f has to be a continuous function. Okay, that's 3.2 on derivatives. See you next time.